So it's my pleasure to introduce the first speaker of the day. Let's see if it's on Zoom.
Yes.
Okay, great. Hi. So Drazen Adamovic is going to talk about indecomposable and logarithmic modules for affine vertex algebras and W-algebras. And everyone on Zoom or in the audience, feel free to ask questions. You can start.
Okay, thank you very much. I would like to thank the organizer for the invitation. So I'm sharing the screen. So can you see the screen?
Yes.
Yeah?
Yes.
Yeah.
Yeah. Sorry. This is better.
Yeah, that's good.
Okay. So thanks again for invitation. So I will speak about certain aspects on the representation theory of vertex operator algebras of affine type and W algebra, and it is mostly motivated with my recent work with various group of people. So this is sorry. So this is So essentially, I will be concentrated on this non-semi-simple part of the story about representation theory of some non-rational vertex operator algebra. So mostly coming from the affine algebra and for W algebra. So what is essentially one of the main goals in VOS theory? So we want to discuss about the representation theory of the simple affine vertex operator algebra associated to any Lie algebra or Lie superalgebra. And this is somehow related to yesterday's talk of David Rideau. He called this exploring high rank logarithmic conformal field theory. So essentially, this is the same problem. So essentially, David gave some explanation of the work in last 15, 10, 20 years in this direction. And essentially, we are doing in similar direction, but we are different persons. So we can have different point of view of studying such things. So essentially, mathematics. So this problem is well defined in both language in mathematics language. So somehow this is related to the representation theory of affine Kac-Moody Lie algebra, and this is conformal field theoretic approach, which was mentioned yesterday by David, with very deep motivation coming from physics and mathematical physics. So, but essentially, object is mathematically well defined. So this is affine vertex operator algebra. This is special representation of affine Kac-Moody Lie algebra. So most natural way for studying such VOA is to apply a representation theory of affine Kac-Moody Lie superalgebra. So we have huge machinery of the representation theory, and this is one exploration of the possibility to apply a representation theory, or maybe more Lie theoretic methods for studying this vertex operator algebra. And what happened? And at the beginning of the story, so I started this was a topic for my PhD, so it's a very ancient story. So then we just have this Lie theoretic method. So what is Katz's book on infinite dimensional Lie algebra and some other approach. And what happened? We can use the representation theory of the special infinite dimensional Lie algebras and Lie superalgebra. And what is the story now? This is excellent and very recommended for exploration of admissible affine vertex operator algebra. And so this is good to study, but to study a certain category, which is also very natural, Gelfand category O, for this affine vertex operator area. So this can be studied. Very much in detail using representation theory, theoretic methods. But now, from certain reason, also explained a little bit motivation by David yesterday. So we need to consider some huger category. We should go beyond the category, beyond this highest weight category. The next candidate is this relaxed category. So we just relax this highest and allow modules which are not a highest weight module. And what is the surprise? There are no clear character formulas obtained by the representation theory. So this is also, I think, one challenge for the representation theory to explore and get this character formula, but this is quite surprising. We cannot use anything from any help from this another universe. So essentially, character formulas which are used here and the realization one needs to somehow derive this formula and everything by vertex algebraic methods. So this is when we go beyond this usual category. So we are in an empty universe. So we need to by hand calculate characters and so on. And the second surprising thing is, at admissible vertex operator algebra, it's well known that maximal ideal is generated by one singular vector, and everything follows from the Katsuaki-Moto formula, character formula. But when we go beyond this admissible level, there are no character formula even for the simple quotient of this VKUG obtained by usual representation theory. So somehow this is two kind of problems which we need to solve. For admissible levels, we can go beyond the category O, and if we want to study ordinary module, we need to explain everything: ordinary modules, characters, generator of maximal ideal, and so on. And so, but there is one promising methods developing last, let's say, 5-6 years ago, that one can apply W-algebra theory for affine VOAs. So this is somehow surprising, because W-algebra seems to be much more complicated than affine. Affine Lie algebra, any PhD student can learn what is affine VOA maybe in the first month of learning, but what is W-algebra, one needs much more effort to learn. But the philosophy now is somehow changed, that we can use W-algebra to study affine Lie algebra. So in some special cases, W-algebra will be somehow easier and simpler than affine Lie algebra. Somehow, I will explain later what is the story behind it. And next, so for studying such approach, what is we discovered one new phenomena, so-called collapsing levels for affine Lie algebra and W-algebra, and these levels W-algebra collapses somehow, become very, very easy, and on such level we can use some concept to describe representation theory. There is two more concepts. Two more concepts. This is also announced by David. This is free field realization motivated by inverses of quantum Hamiltonian reduction. So essentially, this what happened there. So this free field realization is an ancient story for the in Lie theory, for infinite dimensional Lie theory, and so. And question is that we noted that some of representation for which we have very nice free field realization, for other no. And now we essentially trying to understand what is general answer for some free field realization. And for general realization, one need to use this concept of inverse of quantum Hamiltonian reduction. And what happened that using this language, we can find nice realization of logarithmic and relaxed model. So this kind of modules are very, very important to study fusion rules, tensor category on some very modern aspects of the theory, which was also mentioned yesterday. Okay. Sorry. Okay. Okay. And what about affine vertex algebra and W-algebra? So I will just briefly say, so we start from the simple Lie algebra, the super algebra, then we consider associated affine Kac-Moody algebra, and we have universal vertex operator algebra, and then we can consider simple quotient, and we are essentially interested in this simple quotient VOA. So this is one concept which we are interested, and the second is W-algebra, and we are not considering any possible W-algebra. Here we should consider W-algebra obtained by quantum Hamiltonian reduction from affine Lie algebra. We start from any nilpotent element of Lie algebra, and then apply quantum Hamiltonian reduction, and we get W algebra, VKGF, and we get this is universal, and we have its simple quotient. And so universal is a little bit complicated than usually, and for arbitrary nilpotent element, we don't have nice picture. Nice OP's formula. For minimal case, we have nice OP formula, for general, no. But we are interested in this simple quotient. And then we say that W algebra collapses to its affine Lie algebra if just the simple affine W algebra is just affine part. And such level is called collapsing level, and very interesting levels are somehow described in this lecture. So many levels appearing in this 4D, 2D theory essentially are collapsing levels. So this story is somehow developing in mathematics. Mathematics lasts, let's say, from 2015 or something. And in the case of minimal nilpotent element, this collapsing level are classified in joint work with Katz, Mosseneder, Papi, Perchet, 2018. So in order to classify collapsing level, we use Katz-Wakimoto lambda bracket formula. So as I mentioned, W-algebras are not Lie algebra, but technically one can have for universal OPE formula, lambda bracket formula, and Katz and Wakimoto in his remarkable paper discovered such formula, and we use this, and classify collapsing level for this minimal nilpotent. But in general, OP formula are not completely known. Maybe there's something more, but we don't have such nice formula, or we have, and they're so complicated. So complicated. So studying some general case requires different approach. So when we go beyond minimal, What happened? What happened is what was the? I want to recall our result on classification of collapsing level, but our levels which we get as collapsing are, I think, never admissible. Never admissible. But when we go general for general nilpotent, we can have plenty of admissible collapsing level, and this is a recent important work of Tomoyuki, Jethro, and Moreau. Last year they classify collapsing level in this case using representation theory and some very important new ideas, and essentially somehow calculating size of the representation and asymptotic dimension and so on. For K general, but in some case we want to explore some non-admissible case. Recently, so last September, I was in Rome, and we studied with Pierluigi and Paulo some cases, and it turns out that we can solve this enforced classification of such collapsing level for hook and rectangular type. So for special type of W algebra, but our levels are general. Our levels are general. There are some more. So this is some more explicit cases. So based, which can be based on explicit OP formula. When one has explicit OP formula, one can somehow read from the OP, from the lambda bracket, what are collapsing levels and so on. So this is the approach we did with Ozren and Ivana. And Justine also has plenty of new example how one can use OPs and lambda brackets to get new explicit formula, maybe for B, C, this or G, or maybe now more. But this is everything is now still open and can be developed in many directions. And what I'm happy that people are using different methods, and then so somehow this theory grow up. Okay, and now when we have classified this collapsing level, this is one difficult mathematical problem is classify this. So essentially it's deep in the story about reduction or something. But question is what we can do with this collapsing level. What is the story? Why we need this collapsing level? And so motivation of my talk is that somehow explain how we can investigate how we can investigate affine algebra starting from W algebra. So we are primary focus on the representation theory of affine vertex algebra. This is our primary goal. One goal is how to construct, investigate this category, Kajnalushik category, KLK. This is somehow of size of like category of ordinary module for the affine vertex operator algebra. And now we consider problem studying KLK, Kajnalushik category for LK of G modules. G can be Lie algebra or Lie superalgebra. Lie superalgebra. And in the case of Lie superalgebra, we introduce category KLK affine. This is subcategory of KLK consisting of weight module, because in Lie superalgebra, even theory of affine dimensional representation are much more complicated because we don't have complete reducibility. And recently, semi-simplicity in this category, we studied in this paper with Katz, Mosen, Papi, and Perchet. And what is also one new aspect of this theory, this is now theory of tensor category, was really new revolution in this theory, applying this theory beyond the usual rational cases, and the much work of Edmonton group with starting from Thomas and some collaborators, about tensor category of some logarithmic vertex operator, affine vertex operator algebra. So for example, in this, Thomas Kreutzig and Jinwei Yang use our result on collapsing level to study tensor category of KLK models. And this case is essentially beyond admissible. So it's not covered from any other cases. So only with investigating this category of KLK, one can use this representation, one can use this to get tensor category. As I mentioned, there are no character formula, there are not some theoretical deep explanation of this category. So a representation theory of collapsing level somehow was now only way to study such tensor category. And one remark, so in the case when K, for special case, this category KLK can be finite. And we can speak about rationality in this category KLK, and this will be studied in some other talks during the conference. Any question? Okay, and now a few details about just recall what we really proved in this paper. So if we start from simply algebra. So this is simply algebra, and take level K, which is not a positive integer. Then this category KLK is semi-simple in the following cases. We can prove that they are semi-simple in the following case. If K is collapsing, this is the first case. If K is collapsing level, we can prove that this category is KLK. So essentially, this is nice explanation of some rationality problem or something to describe your category as category of associated to collapsing level. And second interesting, which works for non-collapsing level, if we have the W-algebra, if we have, see here, minimal W-algebra is rational. If this minimal algebra is rational, then again, this category KLK will be finite with finitely many reducibles. And we can have semi-simple category on W-algebra side, and from this W-algebra, we can build up semi-simple category of affine algebra. What happened in Lie superalgebra case? In Lie superalgebra case, situation is much more difficult because of problem which I discussed before. And most of the result we can prove for this category KLK affine, weight category. But some of them we prove also for this non-weight category, but most of them for this weight category. So again, if K is collapsing and we have rational vertex operator superalgebra. But here, so in the case of Lie algebra, we really don't have nice example of non-generic affine VOA, which is not semi-simple. But here, even integrable theory for Lie superalgebra take G be SLN1 and K positive integer. Then this category is not semi-simple. And this category is like, one example is also GL1, famous GL11, but here we can prove for SLN1 that this will have non-semi-simple category of model. This category at the bottom is also very interesting from the point of view of tensor category, because there we have typical modules, atypical modules, and so on. And what happened next? So this is all result. And now one problem is to go beyond of this case, beyond of this case. And see here, we can prove a result from this minimal case. Why? Because in this minimal case, we have Tomoyuki result on vanishing of non-vanishing of this homology. When we go beyond this, beyond of this minimal case, situation become more complicated. But let me just say what we did in a paper last week with Pierluigi and Paulo. So we found disappeared last week in the archive. So we found new collapsing level for this rectangular case. So for this so-called rectangular W algebra, so we take this nilpotent element associated to partition Q to M, and this special level, and then we prove that for in this situation, this level is collapsing. So an infinite series of algebra collapsing to level -1 SLM VOA. But for this level, -1 SLM VOA, we know that this is semi-simple by our previous result. So this was also conjectured in the paper by Arakawa, Van Ekeren, and Moreau. This result we prove by using different methods which we started to develop. What was our method? We first proved that this K is conformal level, and then using result about conformal level, then a lot of generators must vanish because of this conformal level. A lot of W algebra generators vanish. And then we apply certain criterion to show that everything collapse and get. So our proof is very elementary, essentially, very elementary. And we didn't need complete knowledge of OPEs or lambda bracket, but we proved that. But still so this is also from the F-family algebra. So we believe that this scale K could be semi-simple for every collapsing level. So natural conjecture following from that is that this level, or on this level, we have semi-simple category, and then one can expect to get braided tensor category on this case. And what is interesting, so this is, I think, a huge problem to construct new rigid braided tensor category. This is motivated by many aspects, but also independently of this work, we in the special case when M equals to Q equals to 2, we proved with Ivan and Ozan such a result. And this conjecture is true for M equals to Q equals to 2. So we believe that we have, one can get much more difficult, and for that one need to understand more about representation theory. But in any case, we have some candidates, good candidates, for which one can try to investigate the representation theory of this special level, which are not admissible. You can see that they are not admissible and collapsing to non-admissible. Okay, this is somehow first part of my talk. Very slow. So this is about.
Just can I make a quick question? So this semi-simplicity statement you say is known for collapsing level associated with minimal nilpotent. Is that right?
Yes.
Okay.
Yeah. For minimal nilpotent, it's known.
Okay. Thanks.
This is, and for other nilpotent, as far I know, so there are plenty of candidates, but in the literature one can find this case. But this -5/2 SL4. And for other cases, there are a lot of candidates. For example, G2 level -2, so something like that. There are plenty of cases for which one can expect, but okay. But there are various approaches with working in this direction. I think even in Brazil. Okay.
Thanks.
So okay, now I want to go to this logarithmic story. So K category is small category. We are working with non-rational VOS, which has many categories of representation. So in this small category, this representation is like in a rational case, and everything somehow similar. But when we go beyond this category, we need to consider much more complicated objects to calculate projective covers and so on. And I started with this logarithmic vertex operator algebra associated to logarithmic conformal field theory. This is theory developed in the last 20 years. And basics, and this is important because this connection with Kazan-Lushik corresponds with quantum groups. It's also discussed yesterday with David. Examples are triplet vertex algebra. Then there is one also interesting example, so-called logarithmic extension of minimal models. And when I prepared talk, I realized that David Rideau presented example of conjectural logarithmic representation for affine algebra, but just remember one result. Sorry. Just remember what was this was something which is obtained by Azat, Gaitardino, Fagin, Semihatovic, and Punin, I think, obtained in a quantum group by using quantum group size. This is 15 years ago. And Anton and myself, we get such a free field realization of such objects. So logarithmic representations look like this. Look like this. So this is example of this famous central charge zero vertex C2 cofinite vertex algebra. And as you see from David talk, one expects such a representation for affine algebra. So a real challenge is how one can construct such kind of models, but for proving some equivalence about quantum group, we need to get something like this. Sorry. So this is something very classical, and now one need to prove that they are projective in certain category. I learned that there will be progress in this case also. And now we go to this affine algebra, and the problem is how to prove existence of and construction of this logarithmic model for affine VOS. And this is another problem where Lie theoretic methods cannot be used, because you saw this representation, how one can get this by using induction, by using usual methods appearing in induction. Somehow these objects appear naturally in quantum group side, but very difficult to be constructed in affine algebra side. And there are plenty of open problem. If you want to give some open problem to students, then I think influence made a very challenging problem in this direction. So about and what is solved, this realization existence and construction are solved for SL2 and SL3 now. Now, so for SL2, it was in my paper 2019, and in this talk I will speak about SL3 solution, but one can expect such models much general. As I mentioned, difficult to start with some abstract construction and get this. It will be great, but so-called. And what is our approach? And our approach was to get such models, by some new method which we called inverse of quantum Hamiltonian reduction. We just go in opposite side. You just go in opposite side. So this means essentially that we want to get embedding of simple affine VOA in tensor product of some W algebra, for which we hope that it will be easier. That will be easier for collapsing level. This can be even one-dimensional. Tensor with some free field algebra. beta gamma ghost or some lattice view or some half lattice view, something which is called free field algebra, which is well understood, much better understood. So we need to get embedding in this direction. And can we do that? So far, one can solve this for SL2 and SL3. I will present what's happened for SL2 and SL3 just briefly. Just briefly, and this is done in some joint work with some people. And what happened for SL? How to do for SL3? So for SL2, just briefly, for SL2, if J is SL2, then affine double algebra must be Virasoro. There are no other choice. For SL3, affine double algebra can be either Breshatsky-Polyakov or Zamolodchikov. So we have minimal reduction and principal reduction. So we need to do somehow to start, for example, from Breshatsky-Polyakov to get SL3. And what is our free field algebra? Just briefly, so free field algebra, this is algebra also mentioned by David. This is localization of beta gamma. So beta gamma goes, beta gamma vertex operator algebra, or where vertex algebra, or this Victor has some different name for this. So this is and then this is beta gamma, and then this beta by special localization of this beta gamma, we get this algebra pi 0, and we are lucky that this algebra has a really nice, fancy realization. This is done by people in toroidal algebra. Michael Lau is here, Yuli Bilic, and people working in Don Berman Tan introduced for this application, for the purpose of application in toroidal algebra. They introduced this algebra, which we call pi 0, but it's also called half lattice view. Hai Shane work in this direction, Chin Wang, and so on. And this is somehow almost lattice vertex algebra, but one can construct nice weight model for this lattice vertex algebra. So essentially, what is the difference? We take lattice, we have full Heisenberg and just half of the lattice in this description. So this is subalgebra of this lattice view, and inside we have beta gamma ghost. And what happened for SL2? What happened to SL2? In SL2 case, so we have embed for non-integral K, we can embed affine algebra in tensor product of the Virasoro. We know everything about Virasoro. Fusion rules, everything, character formula, even Whittaker models we know for Virasoro. Tensor with this pi 0. And then embedding this, the formula are nice. We can get, for example, all relaxed model. We can get Whittaker model, and we can construct for arbitrary admissible level. We can construct logarithmic models of nilpotent rank 2, which is also important for quantum group correspondence. So this is solution for SL2 and C. And now we have complete understanding, almost complete understanding of this. And what happened for SL3, situation is more complicated. For SL3, you see we have two W-algebra. One is Breshatsky-Polyakov, and second is Zamolodchikov, W23. And we did work in 2 steps. This is essentially finding inverses of quantum Hamiltonian reduction in 2 steps. And in general situation is much more complicated. But what happened here? In first step, which I read paper with David and Kazuya Kawasetsu. So we get free field realization of Breshatsky-Polyakov from the Zamolodchikov. So Zamolodchikov W23 or principal W algebra for SL3. They're all named for the same algebra. So we tensor the homological algebra with the same pi zero which we used before, and get embedding of Breshatsky-Polyakov algebra. So, and you see in this formula for G plus is presented. G plus is lattice element. J is some Heisenberg element. For L, we have some Virasoro vector. And for G minus, we have more complicated one. And what we prove that we really have embedding of simples in these two cases, when case neither integer or half integer. Okay, and now we have Breshatsky-Polyakov. And everything what we did for SL2 now can be done from Breshatsky-Polyakov. For example, relaxed module and so. And now we are focused mostly on affine stuff. How to go to affine algebra. So we need the realization of affine SL3. And this is joint paper with Thomas Kreuziger and Nauki Genera. So we construct embedding of a simple affine vertex operator algebra in tensor product of the simple Breshatsky-Polyakov, which we now understand better because we have free field realization using the homological algebra, tensor with free field algebra. And free field algebra in our case will be tensor product of beta gamma ghost with the pi zero, which I explained. So Breshatsky-Polyakov tensor with this two type of VOA, we get back SL3. And formulas are complicated. And this formula, we have some Moreau part is simpler. A1, A2, A3, they are much simpler, but F part is complicated. I just presented slide just to see. It's difficult to understand what is happening in formula, but we really managed to prove, for example, simplicity of the embedding using explicitly working with this terrible formula. So really now we did what we promised. Like we promised that we shall reduce SL3 affine to studying Breshatsky-Polyakov times free field algebra. And now we can explore. What happened. And first step was exploring what are modules in KLK. And we proved that this inverse functors and quantum Hamiltonian reduction and functor and inverse functors are well defined on the category on KLK. They map one KLK to another KLK. So every module for Kazan-Lushik category has the form of one C-wine cofinite module for the Breshatsky-Polyakov, tensor with S, tensor with some extension of this pi zero, and take maximal integrable part, or kernel of scaling operator, the same and we can reconstruct each module from the KLK. And from this, we can essentially reduce and play game between fusion categories for Breshatsky-Polyakov and fusion category for SL3. So this is one step in order to get ordinary module. In order to get a relaxed module, for relaxed module, I will just briefly, we essentially take one other copies of this pi zero. So we need to take another copy of pi zero, and then we can consider weight category of this tensor product of two copies of pi zero. And then our basic concept was here. So we start from the module from the Breshatsky-Polyakov. Here, so you see here, sorry. Module from the Breshatsky-Polyakov, tensor modules with this pi 0 and beta gamma ghost, and we get, and this is our basic object, tensor product of the module from Brzezinski-Polyakov, tensor product with the weight module for pi 0 square. And we get plenty of SL3 modules, FSL3 modules. Some of them will have finite dimensional weight spaces, some of them will have infinite dimensional weight space. And everything will be measured by the size of Brzezinski-Polyakov module. And essentially we get the following answer. So we get the family of and under certain condition, but condition is the top component is irreducible for SL3, we get family of irreducible modules. And we can reconstruct a family, lot of Gelfand-Zetlin modules. So we can reconstruct, so essentially for each n greater than 0, there exist modules such that top component will be Gelfand-Zetlin irreducible modules with all n-dimensional weight space. This is Slava, Futorny, and collaborator speciality of this module. And we can even get modules with infinite dimensional weight spaces. And how to get module with the infinite dimensional weight spaces. So for such guys, we can have character form. They can use being a Berliner formula or something, but we can even construct much more complicated module. So we start with the module for Brzezinski-Polyakov, for which top will be infinite dimensional, which we construct with David and Kazue, and tensor with this pi 0 start. And we get some non-Gelfand-Zetlin modules with infinite dimensional weight spaces for SL3. They are also studied recently in the representation theory. So such modules are even complicated for simple SL3. So we believe that using such realization, we can reconstruct everything. But still, this is work in progress. So we can completely understand what is happening here. And just briefly, I'm running out of time. So this is about relax. So relax, we have plenty of possibility. Top component can be one-dimensional, can be Gelfand-Zetlin module. Top component can be non-Gelfand-Zetlin module with infinite dimensional weight space. And in order to prove some correspondence with quantum groups or try to understand it, so we are very far from the proof, we need logarithmic modules. We need logarithmic module which should play the role of projective cover of certain module. So how one can get this projective, how one can construct such kind of projective modules? So idea is, again, we start from the Brzezinski realization of simple SL3 into tensor product of Brzezinski-Polyakov, tensor with the beta gamma, tensor with pi 0. So for beta gamma, we have a logarithmic module which appeared in many contents recently. They are studied by Alan and Simon Wood. They are module PS. They are projective in their category F. And we can use these projectives. So the logarithmic module of size 2. And for pi 0, it seems that we don't have interesting logarithmic modules. So then we are focused on module from Brzezinski-Polyakov algebra. And then we prove the following. So essentially, what we say, we will prove logarithmic module of order 2 from Brzezinski-Polyakov, which looks very similar to logarithmic module for SL2. Then tensor with the logarithmic module for beta gamma, and which are close to logarithmic module for symplectic fermion, and tensor with the pi 0 modules, and we get the following. We can construct logarithmic modules of rank 2. And for special levels, for special admissible levels, we can construct logarithmic for all admissible levels where the denominator is greater or equal to 4. We can construct a module for affine algebra SL3 of nilpotent rank 3. And this modules looks like as modules which I presented before for logarithmic extension of minimal models, or similarly like David yesterday presented in his so this is very, very complicated structure. And essentially this is tensor product of logarithmic module for beta gamma with logarithmic module from Brzezinski-Polyakov algebra. Okay. And how I'm running out of time. So we have one method developed with Anton, and we use Hai-Sheng-Li construction, one part of Hai-Sheng-Li constructions, and use this delta operator. So this is some technical result how we can construct module from Brzezinski-Polyakov. So this was essentially very, very difficult part, and still we can expect maybe some more result in this direction, but essentially, so this is the classic one can read from our paper. So start from certain model from homological algebra, and doing some extension, we can construct logarithmic module of rank 2 from Brzezinski-Polyakov, and then combining this module with this beta gamma logarithmic module, we get logarithmic module for rank 3. So this is okay. Any question? And next stuff is, so this is one type of the application. So we have this, as I mentioned, this realization is application in study representation theory, in study relaxed modules, projective modules, and there are plenty of application. I think maybe everything what is done for SL2 now can be done for SL3 using this free field machinery and this construction. And what is also recently was very interesting, it was considered a logarithmic vertex operator algebra. So this kind of algebra are very, very important these days because of this correspondence to 2D and for the theory. And what is this algebra called in the case? So one start from a certain family of C2 cofinite vertex algebra. They are called Fagin-Tipunin algebra. They are generally open problem how to prove that these algebras are C2 cofinite. But we believe that for each G, simply algebra of type ADE, that it should be C2 cofinite. A lot of work was done by Sugimoto, Arakawa student, about this algebra. And the high rank generalization of this logarithmic triplet and doublet algebra, which I mentioned in some talk before and will be mentioned later. And what is magic things? What we can do with our machinery? We can transfer this logarithmic algebra, which are extension of either Virasoro or extension of principal W algebra to affine. So we have affine analogs of this algebra. So for example, when in joint work with Kreutzig, Genera, and Jinwei Yang, we investigate this VP algebra, which is obtained by inverse of Hamiltonian reduction of triplet and doublet algebra. So we have logarithmic version of affine SL2 algebra. Affine2 vertex algebra, we have some deformed version, also deformed version of such algebra. And for example, this algebra was extremely important for proving that certain category of Moreau, certain tensor category of rigid. And question about how one can go to higher rank. And this free field realization, shows that we can really expect to get higher rank analogs, higher affine analogs of eigen-Tipunin algebra. So we conjecture that for each Lie algebra, there exists a vertex operator algebra at this special level, minus h check plus 1 over p, which is extension of this affine algebra, and on each Lie algebra gx as derivation. And using this, one can calculate fusion rules and do a lot of stuff. But unfortunately, we cannot prove existence in general by existing methods. But we can prove this for SL3 by using this free field realization. So we study from eigen-Tipunin. So instead of principal W-algebra, we insert this high rank analog of the triplet algebra, tensor with the beta gamma ghost, and tensor with certain special representation of this pi zero stuff. And we get this algebra VA2P, which is logarithmic modules and which is extension at this specific level minus 3 plus 1P. And as I mentioned, one can expect to calculate fusion rules and a lot of application using such machinery. And one possibility, and other things, this shows why it will be important to find a higher rank generalization. So we find one generalization for SL3, but we expect that one can find generalization for each Lie algebra of type AD, at least for A series. Okay. Thank you very much. And thanks again for opportunity to talk.
Are there questions here or on Zoom?
Let me just check on Zoom. Well, maybe I could ask a quick question then.
Okay.
On one of your slides, you described an embedding from BP to Zamolodchikov times, this one,
yes.
as a sort of inverse Hamiltonian reduction.
So from BP is from, sorry, here. Realization of BPS, this one, that one.
Yeah. So in what, just a naive question, in what sense is this inverse Hamiltonian reduction? If both, because both of the algebras are Hamiltonian reductions for different nilpotents, so it's somehow inverse of a partial reduction, or?
Yeah, this is essentially one expects that Hamiltonian reduction of Brzezinski-Polyakov algebra is homological. Essentially, we explain in SL2 case in paper with collaborators what happened, but I think the same arguments should show that if we can define cohomology directly, and so when you have explicit inverse, then it is not so difficult to prove that then from Brzezinski-Polyakov you should get the homological from this picture. I think maybe abstractly is also. I think somebody work in this direction with reduction in steps, but this is essentially of this step.
Okay.
And essentially, so for example, for the David student generalized this for this subregular method. Then in this subregular case, you instead of principal SL3, you have principal SLN or something.
Okay, thanks.
But still, this is somehow still technically a difficult part to analyze. So one thing. So so what was motivation here essentially to construct nice representation of Brzezinski-Polyakov. Construct representation of Brzezinski-Polyakov from the representation from the homological algebra. And then, for example, the relaxed module from Brzezinski-Polyakov are tensor product of the irreducible module from this homological algebra with this character of pi 0.
Drozen?
Yes?
Can I ask how you found this realization if it's not a secret?
What?
How did you find this realization?
So what is the how I find this one or first one?
No, the second formula looks quite complicated, but how did you find such a realization?
So I can say for first one, I analyze Wakimoto representation.
So this one is rather understandable, but the second one.
And then we try to find what should be. We essentially guess this form of the form. So this is there are two ways. One can play game with the screening operators. So Brzezinski-Polyakov algebra can also admit representation for free field realization of the Wakimoto type, and then it's kernel of two screening operators, and then these screening operators are essentially the same as screening operators from the homological algebra. So essentially, this also happened here. Happened as SL2 case. So this is so screening operators can obtain here for the SL2 realization is the same or modified, a little bit modified version of the screening operator for SL2. But here, as I mentioned, one can try one time this is very natural that we should get such kind of realization just to try to find constant and get by calculation. But what is conceptual reason should be that we have the same screening operators in Brzezinski-Polyakov like from the homology.
Okay, thank you.
But essentially, so this is why one can expect here and then the screening operator also play a game in the SL3 case.
Thank you for the answers. I guess there are no other questions here, so we can just thank the speaker again.
Thank you.
And we resume at 10:30 after coffee break.
Thanks, Drazen.
Thank you.
Maybe just a quick announcement. Anyone who hasn't paid for wants to go to the dinner and wants to pay, then they should pay sometime today.